Hi everyone, in this video I will show you how to prove that there are infinitely many primes. So before we get to the actual proof, let's just go over what the definition of a prime number is. A number p is prime if it has the following two conditions. The first one is if p is greater than 1, and the second one is if the number p has no positive divisors except for 1 and itself. So now let's get to the proofs. Now let's begin by supposing that q, the variable q, is the product of all prime numbers up to pn, and then we add a 1. So in a formula it would be written like this: q equals p1 times p2 times p3 multiply all the way to pn plus 1. And note that all the pi's are prime. So basically p1 is the first prime, p2 is the second prime, p3 is the third prime. And if we written in numbers, it will be like this. So here 2 will be the first prime number, 2 will be p1, 3 will be p2, 5 will equal p3. Now based on this formula, we can say that q is not divisible by any primes that is less or greater than p of n. Why is this? Now let's suppose that we erase the plus 1 from both of these equations, the q equations. Then clearly we can see that q is then divisible by p1, p2, or p3 all the way to pn, since q is a product from p1 to pn. However, since we have the plus 1 here, the plus 1 acts like a remainder. And since the plus 1 is smaller than the smallest prime, 2, no matter what prime number divides q, the remainder will always be equal to 1. So here are a couple of examples. So for the first example, let's let n equals 3. So that means that q will multiply the first 3 prime numbers. So q equals 2 times 3 times 5 plus 1, and then we get 31. As you can see, if 31 divides 2, it equals 15 with a remainder of 1. If 31 divides 3, it's 10 with a remainder of 1. 31 divided by 5 is 6 with a remainder of 1. And it all has a remainder of 1 because 1 is smaller than the smallest prime number. Now in the second example, if we let the remainder equals 4 with n still being equal to 3, we can see that the answer is 34. However, since 4 is not a prime number itself and is greater than the first two prime numbers, which is 2 and 3, we can see how that the 4 turns into 2 times plus 2 here. And so 34 is divisible by 2. So now that we know that q is not divisible by any primes less or equal than pn, this means that q is either a prime number, where it can only divide 1 or itself, or it is divisible by another prime, let's call it pk, where pk is greater than pn but less or equal to q. So there are two cases shown here, and in both cases, it suggests that there exists a prime that is greater than p of n. And thus we have infinitely many primes.